Last class, we talked about rational functions, which again is a polynomial divided by another polynomial. And we saw for the rational functions that we looked at, when the degree on top and bottom was the same, we had a horizontal asymptote that was equal to the fraction or quotient between them. So for example, and I'll just write over here for a second. This function, not this one, this function g of x equal to 3x squared minus 15 over 2x squared plus 8. This would have a horizontal asymptote at y equal to 3/2 because the degree on top and the degree on the bottom are both 2, and the quotient of those leading coefficients is 3 over 2. In a similar way, h of x equal to 3x squared plus x minus 1 over 2 plus x squared plus 4x to the 5th. This rational function, right? Again, these are all rational functions because they're all polynomials divided by other polynomials. This rational function would have a horizontal asymptote of y equal to 0 because the degree on top is less than the degree on the bottom, right? The degree on top is 2, the degree on the bottom is 5. The leading coefficient on top is 3, the leading coefficient on the bottom is 4. But since the degree in the denominator is larger, the horizontal asymptote is 0. Another way to think about this, by the way, is that when I'm talking about horizontal asymptote, I'm talking about what's happening to the function as x is getting very large or very negatively large. Well, it makes sense that if the denominator has a higher power, that when x gets really, really large, this denominator is going to be much, much larger than this numerator, which is going to make the fraction very small. For example, if I set x equal to like 1,000, the top is going to be 3 times 1,000 squared, which is like 3 million. The bottom is going to be 4 times 1,000 to the 5th, which is like a million, billion, trillion, a quadrillion. And a million divided by a quadrillion is super small. So that's why this has a horizontal asymptote of y equals 0, because as x gets very, very large, the fraction gets very, very small because the denominator is much larger than the numerator. Well, there's a third case that we didn't really talk about last time, which is when the degree on top is larger. And when that happens, I'm sorry, let me make sure I have all my stuff here. 1 second. So when the degree on top is larger, we don't actually have a horizontal asymptote. And it's kind of for the same reason that I was just talking about. When the degree on top is larger, the numerator is going to get bigger faster. And so the values are going to get really, really big. So they're not going to get close to 0 or close to a number. They're just going to get infinitely large. However, there is one special case where the degree on top is larger that I want to talk about. So I'll come back to this in a second. Let me write another thing here. So slant asymptote, it's also called oblique. Oblique asymptotes. So you get a slant asymptote or an oblique asymptote in the following case. Rational function. So again, polynomial divided by polynomial has a slant asymptote. Only when the degree in the numerator is larger than the degree in the denominator by exactly 1. So only when the degree on top is exactly 1 larger than the degree on the bottom. So the asymptote ends up being, so normally we're used to dealing with horizontal asymptotes where the graph just gets closer and closer to wherever that horizontal line is as you go out either direction. But now we're going to have a slant asymptote, so like a straight line, but slanty. And the function is getting closer and closer to that. So it's an asymptote is a line like y equals mx plus b. Here's how we find them. So to find the slant asymptote, first you have to identify that you have one. So this function here, f of x, equal to x cubed plus 4x squared minus 2x plus 6 over x squared plus x minus 3 does have a slant asymptote because the degree on top is 3, the degree on the bottom is 2, so the degree on the top is exactly 1 larger, which is exactly the time when we have a slant asymptote. So then, once we've identified that we have a slant asymptote, we have to find it. And the way you find the slant asymptote is by doing polynomial division. So I'm going to divide x cubed plus 4x squared minus 2x plus 6 minus, I'm going to divide that by x squared plus x minus 3. And polynomial division works a lot like regular division. Like, so if I was dividing, I don't know, 927 divided by 4, I would be asking, what do you multiply by 4 to get to 9? And the answer is, well, 2. 2 times 4 is 8, and you subtract, and that might take 1, bring it down to 2. And you say 4 times what equals 12? We're going to go 3. 3 times 4 is 12. Subtract, you get 0, bring down to 7. 4 times what is 7? 1, 4. 4, you subtract, you get 3. And you would keep going, and depending on what, so usually you would stop with the remainder when you're trying to polynomial division, but you could keep going and get the decimal. But the point is, same process. You're like, what do you multiply by something to get something, and then you're eventually going to get a remainder. Where, in this case, the remainder is when the number here is less than the number that you're dividing. In this case, it's going to be when the degree is less. That's when you're going to stop. So, the question we're going to ask is, what do we multiply by x squared, the highest power thing here, to get x cubed? And the answer is x. So x times x squared is x cubed. And then you have to multiply by all the other stuff. So x times x is x squared. X times negative 3 is minus 3x. And then we subtract. X cubed minus x cubed is 0x cubed. 4x squared minus x squared is 3x squared. Negative 2x minus negative 3x is negative 2x plus 3x, which is 1x. I don't usually write this term, right? But I want to point out that if you get nothing, that's why we picked x here in the first place. So I usually don't write the zeros. And then we bring down the next term and repeat the process. So then we ask, what do you multiply by x squared to get 3x squared? And the answer is 3. And as soon as I write down that 3 there in the top, that constant term, whatever it is, I stop. That's all we have to do to find the slant asymptote. My slant asymptote, or oblique, is the line y equals x plus 3. And so if I was graphing this thing, which we're going to get to eventually, where you graph this, and you have an asymptote that has a y-intercept of 3, and an x-intercept of negative 3. And it's not actually part of the graph, but it would be something the graph will get close to as we go out to infinity or negative infinity. So that's kind of the idea there. And the reasoning behind this is, well, so I really want to stress, because I want this to be clear. If you're doing the polynomial division to find the slant asymptote, which is really the only way to do it, you really want to stop once you get mx plus b. Once you've written down what the b term is there, you're done. You don't have to do more work. But I'm going to show you why it's true by doing the rest of the work. So if I was actually doing just polynomial division for the sake of doing polynomial division, I would continue on. I'd multiply the 3 by all this. So I get 3x squared. 3 times x is 3x. 3 times negative 3 is negative 9. I would subtract. 3x squared minus 3x squared is 0. X minus 3x is negative 2x. 6 minus negative 9 is plus 15. And this is my remainder. And then there's a theorem about how you can rewrite the division here. So if you divide things, I should have left up my 4 example. In fact, I'm going to recall. So just like we did 4 into 927, and we got, let me think for a second here, we got 2, 1, we got a 3, 12, and we got the 7, 2. Sorry, and the remainder was, sorry, I know this is messy. The remainder was 3. When you do 927 divided by 4, you can write it as 231. plus remainder over divisor, 3/4. Or some of you might want to write this, although you shouldn't write it using a mixed fraction. Another way to write this is 231 and 3/4, like this. Again, we don't really like to write mixed fractions because it's not clear if you mean multiplication or something else. So I would encourage everybody not to write mixed fractions. I don't think anyone is anymore, but just want to point out. But the point is that when you do division, when you divide the top thing by the bottom thing, you can write it as the quotient, this right here, plus the remainder divided by the divisor. The same is true for polynomial division. I can rewrite this function as the quotient x plus 3 plus the remainder negative 2x plus 15 divided by the divisor, x squared plus x minus 3. And the only reason I point this out is because then if you think about this, if x is getting very large, the numerator has a higher power than the denominator. So if x gets very large, this whole thing gets very, very small. And the function gets closer and closer to being this because this part becomes negligible. So that's the reason why this works the way it does, is because when you do this division, you get the quotient, and then you get some leftovers that end up not really mattering. But again, really for just doing the work, all you have to do is get to this quotient here when you get to the 3 or whatever the constant part is and stop. That's your slant asymptote. Questions about that before we move on to some examples? So let's see here. So actually just a few not graphing examples quite yet, but let's look at just a couple. Let's say like we have f of x equal to x squared over x squared plus 3x plus 1. So does this function have a horizontal, does the function have a horizontal or a slant asymptote, or neither? It's x squared over x squared plus 3x plus 1. Horizontal or slant?
Horizontal.
Yeah, definitely horizontal, because the degree on top and the degree on the bottom are the same. The horizontal asymptote here would be y equal to 1. I really should write y equal to 1 over 1, right? That's 1. Or we could look at something like g of x equal to x minus 1 over x squared minus 4. This would definitely have a horizontal asymptote as well. But this one would be y equal to 0. Because the degree on top is 1, and the degree on the bottom is larger, it's 2. Or we could look at something like, what have I got there? F of x, I'm going to change it slightly, equal to 3x squared over x minus 2. Definitely has a definitely does not have a horizontal asymptote. Definitely has a slant asymptote because the degree on top is 2 and the degree on top is on the bottom is 1 smaller. So as long as the degree on top is 1 larger, you have a slant asymptote. To find it, we have to do a little more work. So I'm going to divide 3x squared by x minus 2. Now, whenever I'm doing my polynomial division, if I'm missing powers of x, I like to fill them in. So I'm going to fill this in as 3x squared plus 0 times x plus 0, just to make the process easier. And then we ask, what do you multiply by x to get 3x squared? I'm going to multiply by 3x. 3x times x is 3x squared. 3x times negative 2 is negative 6x. Then we subtract. Some people like to do this thing where they switch the signs. I have never liked that, but you can if you really want. I really hate it, but you can do this. Like, I don't hate it if you do it. I just hate doing it myself. But you can do that and say, like, okay, it's going to be 0. It's going to be 6x. I can't even let myself leave it on the board. It just feels so wrong. It's minus 3x squared minus 6x. So 3x squared minus 3x squared is 0. 0x squared, but I'm not going to write that. And 0x minus 6x is 0x plus 6x, which is plus 6x. Bring down the next term, even if it's a 0. Repeat the process. What do you want to put x to get 6x? Oh, it's 6. We're done. We don't continue the process. Our slant asymptote is y equal to 3x plus 6. You could continue the process, but there's nothing else to really be gained if you're going to be graphing it. Okay, so let's do some examples. Let's graph some things. So I will say, right, just like last class, the process for graphing a rational function is going to be the same. We're going to find the Y-intercepts, we're going to find the X-intercepts, we're going to find the vertical asymptotes, and we're going to find either the slant or the horizontal asymptotes. And then we're going to graph the whole thing. So still very, very much the same thing we were doing last class. It's just that now we're going to have some graphs that have slant asymptotes instead of horizontal asymptotes. And you can only have one or the other for a rational function. You can't have both a slant and a horizontal asymptote. You can only have a horizontal or a slant. Or you can also have neither, but we're not really going to deal with those in this class. You could have neither if your power on top was a lot larger, like if it was a x to the 4th over x squared. That would be not a slant asymptote, but still not having any asymptote, really. So let's look at this example. We want to graph f of x equal to x cubed over x squared minus 9. Okay, and let's do all the usual stuff. So first, the y-intercept. I'm going to set x equal to 0. We're going to get f of 0 is 0 over 0 minus 9. 0 divided by a non-zero number is 0. Right, negative 9 goes into 0, 0 times. X-intercept is also not very exciting. It's also going to be 0. So I'm going to remind everybody, and we can go through this again if you want me to. Please ask. To find the x-intercept, instead of setting the whole thing equal to 0, we're just going to set the top equal to 0. So I'm going to set x cubed equal to 0, and immediately I'm going to get 0 as my answer. So not surprising, if my y-intercept is 0, one of my x-intercepts is also 0. In this case, my only x-intercept is 0. So great, so far we've got 1 point. Let's find the vertical asymptotes. So I'm going to set the denominator equal to 0. So I'm going to set x squared minus 9 equal to 0. And I want to say something here that I didn't talk about last class, but I do think is worthwhile. Instead of adding 9 to both sides and taking the square root and getting x equal to plus or minus 3, which is a totally valid way of doing it, I would rather factor. And I'd rather factor because it kind of tells me something extra. So I get x minus 3 times x plus 3 equal to 0. We still get the same solutions, right? Still get x equal to 3 and x equal to negative 3. But I actually want to point something out. And actually, I forgot to say this also. So our x-intercept came from setting x cubed equal to 0. That's going to have a multiplicity of 3. Which means for our x-intercept, since it has an odd multiplicity, we're going to cross from either above to below or below to above the x-axis. Well, here's the thing. Vertical asymptotes have the same sort of thing being true about them. Meaning, if a vertical asymptote comes from a factor with an odd power, we can talk about the multiplicity of that vertical asymptote. This vertical asymptote and this one, they both have multiplicity of 1. Which means we're going to cross from being below to being above the x-axis, or vice versa, from being above to being below. Which means for asymptotes, these are going to look like this. one side's going to be up to infinity, one side's going to be down to infinity. If it was an even instead, they'd both be going the same way because we wouldn't cross. We would stay on the same side. So they'd both be going up or both be going down. We'll see that. I'll definitely say more about that as we continue with this problem. The last thing is, do we have any sort of horizontal or slant asymptote? Well, yes, we do. We have a slant because the degree on top is 1 larger than the degree on the bottom. So we have to do the polynomial division. So I'm going to fill in the missing powers for each of them. So x cubed is what's being divided into, right? The higher power is always the thing that goes under the, there's a name for this symbol. I don't know what it is. Under the division symbol. And that's going to be x cubed. And then all the powers that are missing. 0x squared, 0x, 0. And then into it, I'm going to write x squared. I'm missing the x term, so now there's plus 0x minus 9. Okay, so I'm going to multiply. Well, I'm going to figure out what to multiply. What did I multiply by x squared to get x cubed? Anybody? Anybody? Exactly. X times x squared is x cubed. X times 0x is 0x squared. X times negative 9 is negative 9x. We subtract. X cubed minus x cubed is 0. 0x squared minus 0x squared is 0. 0x minus 9x is plus 9x. Bring that to 0. And now look, we're actually done. Because x squared is a higher degree than 9x to the first. So once we get to this place where the degree here is less, this is our remainder. So our slant asymptote is just y equals x. All right, so let's turn the board and put it all together. Which, I mean, there's not a lot. There's the 1.00. There's the vertical asymptotes 3 and negative 3, and there's the slant asymptote y equals x. Okay, so again, we're graphing y equal to x cubed over x squared minus 9, which I'm also going to write as x cubed over x minus 3 times x plus 3. Just to help you guys see all the things. Let's go 1, 2, 3. So here's the thing about slant asymptotes. Just like horizontal asymptotes, they don't really care what's going on in the middle of the graph. They more distinguish or determine what's happening as you move way out to the ends on either side. So we're not going to really pay attention to the slant asymptote I'm going to draw until we get to the end. And I'm going to try and draw it in a way so it's kind of graphable. So here's the line y equals x. And yes, all your asymptotes should be drawn as dashed lines. Okay, so now I've really only got 1 point. And I've got the point 0, 0. That's kind of it. I might need to graph 1 more point. So let's look to the right here for a second. If I plug in x equal to 1, y is going to equal 1 on top, and 1 minus 9 is negative 8 on the bottom. I don't really care what the value is, I just care that it's negative. So that when I go over here to 1, I get a small value. And now I'm trapped. I'm on one side of the x-axis. And again, we can't cross the x-axis unless we have an x-intercept. So let's see what happens. We're going to go down this way. We're going to have to get very negatively large because we can't go up because we can't cross the x-axis. But now here's what I want to say. On the other side of this asymptote, this vertical asymptote, we're either going down this way or up this way. And we have to be going up for 2 good reasons. One reason, what I said before, which is kind of a new thing, is that this asymptote, x equal to 3, this asymptote, x equal to 3, came from this factor, x minus 3, which has an odd power. And when vertical asymptotes come from factors that have odd powers, they have opposite signs or opposite directions, right? So I usually say, oh, odd power means opposite direction. Oh, they both start with O. So one side has to go up, one side has to go down. So since this side is going down, this other side has to be going up like that. There's no other choice. The other way we know it's true is because if we were down here, we'd have to cross the x-axis to be able to get closer to our asymptote. And we do have to get closer to our asymptote as we move out to the right. So what happens is we're going up this way, and then we slowly maybe come back down, and then we have to turn around so that we're getting closer and closer to our slant asymptote. You can also test a point, right? If you want to test like x equal to 4, if you plug in 4, the top is 64, the denominator is 16 minus 9, which is 7. And I don't really care what that number is, I care that it's positive. 64 over 9 is definitely positive. Okay, on the left-hand side, well, we know that this X-intercept has an odd multiplicity, so we're going to cross. So we're going to be going up this way. And then we know that this vertical asymptote also has an odd multiplicity. So if one side's going up, the other side has to be opposite and go down. And then it's going to come up and then eventually get closer and closer to the slant asymptote. So if you zoom way out on this, it kind of just looks like the line y equals x. In fact, I would like to show you on Desmos just for a sec how that kind of looks, because I think it's worthwhile. I might show you two things. Or maybe nothing if my computer actually doesn't want to go there. There we go. Okay, sorry. Graphing calculator. So if we look at this real quickly here for just 1 second, here's the graph of x cubed over x squared minus 9. And if you zoom out, in fact, if you zoom way out, it just looks like the line y equals x. Right? So that's what I mean when you say something about an asymptote, is that the function really just looks like that asymptote if you move way out to x being really, really large or x being really, really negatively large. It's only when we zoom in, where the middle is like, oh, the middle is actually kind of funky. There's other things happening there. But the slant asymptote here really is telling us, oh yeah, the function is essentially just like that, except for when the middle here, when things are all crazy. It's also true for horizontal asymptotes, right? If I graph something like something easy, like easy meaning it's easy to tell what the horizontal asymptote is, like y equal to something like, I don't know, 2x squared minus 2 divided by, oops, I always make that mistake. Let's put some parentheses around it. Divided by, I don't know, 3x squared plus 4. We can see here, oh yeah, there's definitely a horizontal asymptote, right? I mean, we have to zoom in to kind of even be aware of it, right? So right in the middle, okay, it's just kind of doing its thing. But as you zoom out, you can see, oh yeah, this function is definitely getting closer and closer to the horizontal asymptote, which is y equal to 3/2. 3/2, that's not right. What should it actually be? It should actually be 2/3. Right? I flipped it over accidentally. Right? We can see that, oh yeah, that function is, I mean, it doesn't take very long for it to get really close to the 2/3 value. They're essentially the same. They're not actually the same, but they're very, very close to each other anywhere that's not even remotely in the middle, right? We're just like, oh yeah, they're super close. You can zoom in, you can see there's still, right, this the green one, the 2x squared minus 2 over 3x squared plus 4 is always going to be a little bit lower, but like not a lot, right? There's the green y value, there's the purple, right? They're within 1/100th of each other right there. And as you go on, it just gets more and more nutty. Anyway, that's what I wanted to say. Oops, can I even click on the other one? There we go, yeah. Right, they're very close in value. So that's what I mean when I say something is getting closer and closer to its horizontal asymptote. I mean, the y values of the function are getting very, very close to the y value, to the actual horizontal asymptote value. It's just when they're slant asymptotes, you're not getting close to a particular value, you're just getting close to a slanty line. I should also say, just because it is interesting to note, this function is an odd function. It has rotational symmetry. Right? If you rotated this 180 degrees, it would look the same. And we can check that by checking that f of negative x is, I'm going to plug in a negative x for every x. So it's negative x quantity cubed over negative x quantity squared minus 9. And that's, so negative times a negative times a negative is negative. So it's negative x cubed over a negative times negative is positive. And although that's definitely not the function that we started with, it is equal to the negative of the function we started with. This is definitely equal to negative x cubed over x squared minus 9, which is negative f of x. I do want to point out, I don't think I saw anyone make this mistake in the homework, but I just want to mention, right, when I say you have like the negative of a function like this and it's a fraction, you can't distribute the negative to both the top and the bottom. That's like multiplying by negative 1 over negative 1, which is really like multiplying by positive 1. I can only multiply either the top or the bottom by negative 1. If I multiply the top by negative 1, I'm like, oh yeah, it's just that. So yes, this is an odd function. It has odd symmetry. Let's look at more examples. Where are my examples? There we go. So that's the process, right? We're going to find the intercepts, find the asymptotes, maybe plot an additional point or two, and graph the thing. And again, I would also say you are welcome to look at Desmos to kind of see how you've done. I would really encourage you to try and graph it on your own without looking at Desmos first. But then if you want to see, does my graph look right? You are welcome to go look at other tools, Desmos, graphing calculator, whatever is available to you. You are really welcome to use. So let's look at this next one. Let's look at f of x equals to x squared minus 4 over x minus 1. Which again, we can see has a slant asymptote because the degree on top is exactly 1 bigger than the degree on the bottom. Well, let's find the other things first. So y-intercept. That's going to be, if x is 0, we're going to get y equal to 0 minus 4 over 0 minus 1, which is 4. X-intercepts. Again, we're thinking of setting the whole thing equal to 0, but we know we really only have to set the top equal to 0. So I'm going to set, and again, just in case anyone's forgotten, what I'm really doing is I'm setting the whole thing equal to 0, and then just multiplying both sides by the denominator. When I multiply both sides by x minus 1, on the left, it just cancels out. That cancels with that. And on the right, 0 times the thing is 0. So I get x squared minus 4 equals 0, which I'm going to factor as x minus 2 times x plus 2. So I end up getting x equal to 2, the multiplicity of 1, and x equal to negative 2 with a multiplicity of 1. So I know that at each of these x-intercepts, we're going to cross through the x-axis. Let's go ahead and find the vertical asymptote. Should be pretty straightforward. I'm just going to set the denominator equal to 1, which is going to give me x equal to 1. And then for the, well, I know I don't have a horizontal asymptote because the degree on top is larger. I have a slant asymptote. For my slant asymptote, I'm going to do the polynomial division. X minus 1 into x squared plus 0x minus 4. So x times x gives me x squared. So x times x is x squared. X times minus 1 is minus x. Subtract 0. And then 0 minus x is positive x. Bring down the 4. Oh, sorry, the minus 4. And then what do you multiply by x to get x? Oh, you pick 1. 1 and done. Right? Y equals x plus 1. So there we go. That's our slant asymptote. So it's going to be a slanted line, right? It's going to be a straight line with a slope of 1 and a y-intercept of 1. Okay. Let's graph it. Oh, I should also say our vertical asymptote also has an odd multiplicity, right? It came from a factor that was raised to the first power. Whereas the x minus 2 is also came, or sorry, the x equal 2 and the x equal minus 2 also came from factors at the first power after you factored it out. You do have to sometimes either factor something out or multiply it together to see what the actual multiplicity of it is. Yeah. Okay. Oh, sorry, we're graphing this one. So let's see here. We had a y-intercept of 4, x-intercepts of 2 and negative 2. Vertical asymptote of positive 1. Yes, the vertical asymptote of positive 1. Let's draw it in different colors to be fun. And the slant asymptote of y equals x plus 1. Where did the 1 come from? X plus 1. Sure thing. So, right, so we were dividing x squared minus 4 by x minus 1. We said, what do you multiply by x to get x squared? We did x. X times x was x squared. X times minus 1 was minus x. We subtracted. X squared minus x squared is 0. 0x minus x is 0x plus x, which is x. And bring down the minus 4. And then we say, what do you multiply by x to get x? Oh, it's positive 1. And then if we were going to finish the process, we would say 1 times x is x. 1 times negative 1 is negative 1. And you would subtract 0, negative 4 plus 1 is negative 3. We don't usually do this part because we don't need to, because we can stop once we get to the constant term there. So that's where the 1's coming from. And the fact that 1 times x equals x. So our slant asymptote is y equals x plus 1, which has a slope of 1, a y-intercept of 1, and an x-intercept of negative 1, right? We're doing y equals x plus 1. The y-intercept is 1, the x-intercept is negative 1. Again, those aren't really points that are on my graph, they're just points that help me draw the slant asymptote. That looks all right. And now we're going to try and graph the graph. So I like to start my y-intercept and then move to the right. So I move to the right, and I come up against this vertical asymptote. I either have to go to infinity or negative infinity, but I can't go down to negative infinity because I can't cross the x-axis without an x-intercept. I can totally cross the slant asymptote. It doesn't happen all the time, but it does happen sometimes. But I can't cross an x-intercept, an x-axis if I don't have an x-intercept. So we have to go up this way. And then we said that our vertical asymptote came from a factor with an odd power, which means one side goes up and the other side goes down because they do opposite things. We hit our x-intercept and we cross. And we get closer and closer to our slant asymptote. And then we go back to our y-intercept and we move to the left. As we move to the left, we're going to hit our x-intercept, we're going to cross, and we're going to get closer and closer to our slant asymptote. That's not the best I've ever drawn that, but I think you guys get the idea. You're like, yeah, but you could draw it better. You're like, you're right, I could. Sure. Not my best. So that's what's happening there. Getting closer and closer to the slant asymptote as we move further and further. So again, if you zoom way out, the middle would just kind of start to disappear, and this would look a lot like y equals x plus 1. If you don't like this thing that I am doing, where I'm saying, you know, I'm going to talk about the multiplicity of the asymptote, you can also do the thing where you make a little number line. You say, okay, well, on the number line, the places that are important are the x-intercepts and the vertical asymptotes. So that's 2 and 1 and negative 2. And the function was y equals x squared minus 4 over x plus 1. We want to see where it's positive and where it's negative. So pick a number larger than 2, like 3. And I might even factor the top, so it's x minus 2 times x plus 2 over x plus 1. Plug in 3, positive, positive, positive. Plug in something like between 1 and 2, like 1.5, negative, positive, positive. Plug in something between negative 2 and 1, like 0. We already know it's positive at 0. And then plug in something like negative 3, and it's going to be negative, negative, negative. It's negative overall. And look, our graph meets that. It is negative over here, left of negative 2. It's positive between negative 2 and 1. It's negative between 1 and 2. And it's positive after 2. So you can do this number line thing if you're not a fan of what's the multiplicity of the vertical asymptote. I personally am a fan. That's why I talk about it. But you don't have to be. Yeah, let's do that one. Sure. And then we might not get to the very last one. Yeah, it's okay. Oh, yeah, we'll look for that. So we'll do the very last one then. Sure, let's graph this one. Yeah, let's do that one. Let's do f of x equal to x squared times x minus 3 over x minus 1 squared. I'm going to do this one quick. So, y-intercept. X equals 0, y is going to be f of 0, which is going to be 0, because if you plug in 0, that's going to be 0, and 0 times anything is 0. X-intercepts, we're saying the top equal to 0. So x squared times x minus 3 equals 0. We already know x equals 0 is going to be one of them, with a multiplicity of 2, which means we're going to bounce. We also are going to get x equal to positive 3, with a multiplicity of 1, which means we're going to cross. Vertical asymptote, set the denominator equal to 0. We're going to get x minus 1 equals 0. We're going to get x equal to 1. But it's going to have a multiplicity of 2, meaning unlike our other vertical asymptotes where one side has gone up and the other side has gone down, now either both sides are going to go up or both sides are going to go down. They're going to do the same thing except the opposite thing. It's like bouncing off the x-axis because we're staying on the same side of the x-axis. Just like in the other examples, which I think I've erased. All right, like here, right? The vertical asymptote having an odd multiplicity means we cross from being above the x-axis to being below the x-axis, just like we do in an intercept, where we have an odd multiplicity. Okay, and then finally the slant asymptote. So to find the slant asymptote, I really need to multiply at the top and the bottom. So this is equal to, so you multiply at the top, x squared times x is x cubed. X squared times minus 3 is minus 3x squared. The bottom, x minus 1 squared is x squared minus 2x plus 1x. We're foiling out the x minus 1 times x minus 1. So the slant asymptote, I'm going to do this division. I'm going to do x squared minus 2x plus 1 divided into x cubed minus 3x squared plus 0x plus 0. Okay, what do we multiply by x squared to get x cubed? X. X times x squared is x cubed. X times negative 2x is negative 2x squared. X times 1 is x. Subtract. X cubed minus x cubed is 0. Negative 3x squared minus a minus, so plus 2x squared is negative x squared. And 0x minus x is minus x. Bring that to 0. When you multiply by x squared to get negative x squared, negative 1. Negative, we can stop there. So y equals x minus 1 for that asymptote. Okay. So let's graph this. And then maybe, I don't think I have time to do the very last one, but I can look at it with you guys for a minute and we can kind of talk through it. Because it should, there's something about the other example that I'm not going to do that I think you guys should see. So graphing this one. forget what's what. Let's double check. So we have, let's see, Y-intercept is 0, X-intercept is 0, and 3. Vertical asymptote of 1. Okay, so 0 and 3 are intercepts. Vertical asymptote of 1. I said 1. Yeah. X equals 1. And a slant asymptote of y equals x minus 1. So it's going to have a y-intercept of -1 and an x-intercept of positive 1. So it's going to go through those 2 points there. Okay. So, let's start here. And now the problem with starting at the origins, we don't know if we have to go up or down. So let's pick one more point. Let's pick a point like, let's actually go left. Let's pick a point like -1. If I plug in -1 to y equals x squared times x minus 3 over x minus 1 squared, if I plug in -1, I get -1 squared, so 1 times -1 minus 3, -4, over -1 minus 1 squared, which is -4 over positive 4, which is -1. So I assume the point -1, -1. And now we know a lot. So I'm going to go this way, and then I'm just going to get closer and closer to my slant asymptote. To the right, here's what's going to happen. We know at the origin we bounce off because it was an x-intercept of multiplicity 2. So what's actually going to happen is we're going to bounce off and we're going to have to cross our slant asymptote. It does happen sometimes. And then go down that way. We said our vertical asymptote had an even multiplicity, meaning if one side's going one way, the other side's going the same way. So if the side's going down, the other side's also going down. You can also plug in a point like 2 and see that it's a positive times a negative divided by a positive, so the whole thing would be negative. We're going to hit this intercept, we're going to cross like that. That's what that one looks like. So let me show you one more example that's in the notes. I know we only have a minute left, but I do want to show you this last one just because there's one important thing that I should mention. So let me share my screen real quick. So here's this last example, which is x minus 2 cubed. And let me zoom in a little bit because I feel like it's kind of small. I don't know, maybe it's not so small. So x minus 2 cubed over x squared minus 5x plus 6. And something that we should be doing all the time, which we haven't had to do so far, is to factor first. So here, if you factor out the bottom, it factors as x minus 2 times x minus 3. And then you can actually cancel one of the x minus 2 factors, which means that we have a whole of x equal to 2. Meaning we're going to graph it just like normal, but then after we graph it, we're going to say, oh, except when x equals 2, you actually don't have a point there. So we still do all the normal things with the simplified one. We find the y-intercept by setting x equal to 0. We get 4 over -3, which is -4/3. We find the x-intercept by setting x minus 2 squared equal to 0, the top equal to 0, which gives us x equal to 2. But then we're like, oh, we're going to have a hole there actually, but we would still kind of plot it and then take it away. Vertical asymptote we get by setting the new denominator, right? So we don't want to look at this one over here because that would give us a wrong vertical asymptote of x equal to 2 and x equal to 3. We actually need to look at the factored and canceled form and see that the vertical asymptote is only from setting x minus 3 equal to 0, giving us x equal to 3. And then finally, the slant asymptote by dividing, and you can divide either one, but it's easier if you do the simplified one. If you divide x minus 2 squared, which is x squared minus 4x plus 4, by x minus 3, you get x minus 1. So then here's our graph. It's got a slant asymptote of x minus 1. It's got a vertical asymptote of x equal to 3. It would have an x-intercept at 2, but there's a hole there. And it has a y-intercept of -4/3. So starting at the y-intercept, I would go to the right. I would go up to my supposed x-intercept and then bounce off because it has an even multiplicity, come back this way. My vertical asymptote has an odd multiplicity, so I'm up here and then I'm going this way like that. I go back to my y-intercept and then I go to the left and I have to get closer and closer to my slant asymptote. And then finally, I would erase this point here because it is a hole. Right? So if you plug in 2 to the original function, it's 0 over 0, which is undefined.